So an example of this would be in this picture here. So we have a diver that looks like they're, compressed somehow the diving board. So there's elastic potential energy, or that stretched kind of springish energy in the diving board, and that's going to be released or transferred into a different part of our system, into the diver. So the diver is going to gain kinetic energy because the board is moving and the diver is going to start moving. And then the diver is going to leave the board and go into the air. And that would be kinetic energy transforming into gravitational potential energy. So all that energy that is transformed stays within our system. And you define your system. So that's part of the key. So our system would be the diving board and the person and then the earth, because in order to have gravitational potential energy, you need the earth. So energy transfers and work. Transfers are different from transformations, and that's the words that are pretty close that sometimes can be a little confusing. So when energy is transferred, you're taking it from one object and you're taking it and putting it into a second object, or a second system. So energy transferred between a system and its environment or the surroundings through work or heat. All right, so work we've already talked about, and work is just the mechanical transfer of energy to or from a system by pushing or pulling on it. So we've defined work. So again, if like I'm a person, which I am a person, and I was pushing something, so let's say I was pushing a big box. If the box is the system, in the beginning the box isn't moving, it doesn't have any energy, it's not going to fall, anything like that. So that's our system. I'm outside of the system, and when I push on it, the box starts moving, so it starts moving maybe to the right, and the box moves some distance. And we calculated the amount of work that was done. That amount of work that I did on the box is the same as the amount of energy that the box gained. So let's try a situation where we have a spring, which is going to launch this cart like in a roller coaster, and it's going to go around the roller coaster loop, and we're going to compare point A and the amount of energy at point A compared to the energy at point B. And we're going to assume that the system consists of the cart, the earth, and the track, and the spring. Okay. So it says it's frictionless, so I don't have to worry about any heat being generated between the cart and the track. So again, we include the earth in our system here because if we talk about gravitational potential energy, you need the earth there. Otherwise, the earth is outside of the system and it's going to do work on the object. So in the beginning at A, it's at rest, so the kinetic energy is 0. I'm going to say this is the lowest position. It's at like the lowest position here. So we're going to say that it can't fall from that position. So it's got no gravitational potential energy. And it does have the spring potential energy. So I'm just going to make a bar. I don't know exactly the amount. This is just qualitative. So it's just kind of thinking about like the idea. But I have 4 spaces of elastic or spring potential energy there. Non-mechanical energy is that heat and sound, and we're not generating any of that because it's going to be frictionless. So that's 0. At the end, we're up here, and there's these lines that indicate that it's moving. So maybe it's got 2 bars of kinetic energy. It's above the ground, so it can fall. So it's definitely got gravitational potential energy. So I'm going to make that 2 as well. And the spring is still in our system, but it's no longer compressed, so that's going to be 0. And again, we didn't have any heat or sound because of that. So what should happen is whatever you have in the beginning, this is the conservation of energy idea. So we had 4 bars of energy here. We have 2 and 2. So that makes it work out. Now you might ask, does it have to be 2 and 2? It doesn't. We could have made it maybe 1 of kinetic and 3 of potential, or however this distributes, but these 2 added together should get you to 4. So that's just like an idea. So in this conservation of energy, like the total energy in the beginning, total energy at point A, it should equal the total energy at point B. And it does in this case because we have what's called a closed system. So there isn't anything outside of our system doing any work. So we had spring potential energy in the beginning, US. At the end, we had these 2, which is kinetic and gravitational potential. And we'll learn more about these individual energies and how to calculate them through their formulas. But like this concept of like setting the energies equal to each other is an important one, and if you can do that well, then you're going to be okay with calculating energies through conservation of energy, which is the big skill. All right. We talked about mechanical energy a little bit. I just want to talk about it a little bit more to get into the specific types. So again, mechanical energy is energy can easily change or move matter. It can easily do work. So kinetic energy is the first of those two types. So kinetic energy is energy due to motion. The formula for it is here. So it's 1/2 mv squared. Half is just a constant. K is kinetic energy, half is just a constant, m is the mass, and then v is the velocity or the speed of the object, and you got to make sure you square it, okay? Again, the unit at the end is joules, so when you multiply all those things together, you get joules. And it says, using the factors that affect kinetic energy, what would you do to maximize the amount of work? So we're going to do this concept of energy and work are the same thing. It's just, you know, one person, or like it's our system that determines whether it's work or if it's just another form of energy. So so I don't know. I watched wrestling when I was a kid, so I like to use examples with wrestling because it's sort of, you know, it's pretend violence. I do not condone real violence, but it's pretend violence, and it gets you the ideas and the concepts that you want to do. So so if we were taking kinetic energy and we wanted to maximize the amount of kinetic energy that we had, so this person's going to punch this person here, and we want to maximize our kinetic energy. So again, the kinetic energy that the person has in their fist is going to do work on this person's face and make it change or move. And we wanted to what would you do to the velocity to maximize the energy? That's the first question. So what would you do to this v? And again, this is like whether it's directly related or indirectly related. So velocity, it has a direct relationship. It's actually velocity squared. So it's a squared relationship. And if you increase the velocity, so if we increase v, that would cause an increase in the kinetic energy. And that makes sense, right? So like if I wanted to punch somebody, and I wanted to do as much damage or do as much work as possible, I would make sure my hand is moving as fast as I could make it. The other thing that I want to do is I would, with mass, so that's the other factor that affects kinetic energy. And again, you can see they're in the same part of the fraction or equation. So if we increase the mass, that's going to cause an increase in the kinetic energy. So if you imagine, instead of just punching him with like my fist, I had like a brass knuckles, or I roll a quarter or something like that. That would do more damage. So it would do more work. It would cause more change. So those violent or semi-violent, pretend violent examples are good to kind of visualize to keep that stuff in your head. Okay, so that's kinetic energy. The other types of energies that we have are potential. So potential energy is energy of position. So position or configuration. Potential energy is stored energy. It's sort of like the word potential used like when you're talking about a person and their abilities. So like if you talk to like a guidance counselor or somebody, they'd be like, oh, you have a ton of potential. And that means you have like this innate ability to do stuff, but you might not be doing it that exact moment. Okay. So the first one is gravitational potential energy, and the formula for that that I just use is mgh. So m is mass, g is the acceleration due to gravity, that 9.8 number that we've always used, and then h, as long as we're on Earth, and then h is the height above the zero level. So kind of the ground is usually like wherever the lowest place it's going to go to, that's where we call zero. So if it starts out on the ground, this would be the 0 meters, and in order to give it gravitational potential energy, we have to raise it up and give it some height. So that is one type of energy. So we take that mass of m and we raise it to some height, and because of that ability to fall, that's really where it gains its energy. That is the gravitational potential energy. Spring potential energy is the energy stored in a compressed or stretched object. The formula for it, these are the same formula. It's just whether you use this delta x for displacement or x. But it's 1/2 k x squared. K is something called the spring or force constant. And that just describes the spring itself. So like if you imagine different springs, it takes different amounts of force to compress or stretch them. So some are like stronger and some are weaker. That K value is what's describing that. So the stronger the spring is, the bigger that K value. And then displacement for the equilibrium position, that's how far you stretch it. So the further you stretch it, the more distance it changes shape. So again, some examples. So this person is going to jump on this person and land on them. So how would we want to maximize the energy, the gravitational potential energy? So it's mgh. So what are we going to do to this height? So would you just jump on them from a low level or the higher? I think it makes sense the higher. So as you increase h, you're going to increase the amount of mechanical energy in the form of gravitational potential energy. Another one, what did you do to the mass? So again, if you had a light object versus a heavy object, the heavier object, the more massive object is going to be able to cause more change and movement in that matter. So that's one thing. If we're talking about the spring potential energy, let's talk about kind of like this is a Roadrunner cartoon. I know you guys might not be familiar with it, but he uses these contraptions to try to get the Roadrunner. And this is like a spring with a boxing glove. So what would you do to the spring constant? So again, the formula for this one is 1/2 kx squared. K is the spring constant. Again, you can see all these are directly related. So K, if K increases, if it's a stronger spring, it's going to store more energy. So US is going to get bigger. And then the change in position, the X or delta X, depending on how you write it, that is also going to cause an increase in the spring potential energy. I forgot to draw the arrows up here. So they are all direct relationships in all of these formulas so far. Okay. Non-mechanical energy is energy that can't be easily changed into move or matter. So like heat and sound or light, those are all examples that are what is demonstrating non-mechanical. So if if I just yell at something, it doesn't make it it doesn't throw it across the room. So like that's sound energy that is being transferred through the particles that is transferring that sound. It isn't going to make the object move or change very much or easily. Heat, same thing. Heat can do stuff like you can do heat and you can like power a piston, which could cause motion and all that, but it's not a like direct like change like it is for gravitational potential energy or spring potential energy or kinetic energy, which easily does work. Okay. So we can have work done on our system or work done by our system. So it's talking about what is going on. So if this is our system, again, the boundary is the circle. Everything that's in our system has energy. And if something is doing work on the system, if an applied force does work on a system, it tries to increase. So like we're putting energy in. So it's sort of the flow of the energy in or out of the circle. If applied work does negative work, so that's positive work. So if we're adding work to the system, that means the total energy is going to increase. So the total energy at the end is bigger than the total energy initial, and that makes sense. So the total energy that you start out initially with, if you add positive work to it, you'll get an increase in total energy. If we start out with the same total energy in the beginning and we did negative work would be like essentially, things taking energy out of the system. So that'd be negative work there in green. And that would cause a decrease in the energy of the system. So that's total energy final would go down. And total energy, mechanical energy, pretty much the same thing. Total energy, we just incorporate all the energy that's there. If work is being done by the system on the surroundings, then again, the total energy decreases. So it's like the energy is going out of the system. So it's just, we use these flow diagrams. We did it with that roller coaster example. But it's like how the energy is flowing. So if energy is coming in, it's going to make it go up. If energy is going out, it's going to make it go down. All right. So this is called the work energy theorem. And we've kind of stated this already, that the network done on all, or the network due to all the forces acting on a system equals the change in the energy. So when we did this is sort of like the work. So if I do this, the work is equal to, if I take the total energy to the other side, I'll get change in energy, change in total energy. That's the work energy theorem. So you can look at it through this concept here with work is change in total energy, or we can talk about it in terms of the energy in the beginning compared to the energy at the end. It's just conservation of energy. We didn't talk about this example, so I'll skip over that and keep going. All right, so we've talked about a lot of different types of energies. This chart just summarizes those ideas and gives you an example of them. So again, kinetic, gravitational, elastic potential, those are all mechanical energies. So these three all fall into mechanical, or I'm sorry, I drew to the wrong spot. Mechanical energy. Again, the formulas are there. So mechanical energy is all the kinetic plus all the potential. Non-mechanical energy is the heat and sound energy. It's work done by non-conservative forces. Friction would fall under that. So like the work done by friction changes things into heat and sound. So that's non-mechanical energy. To find work, we do FD cosine theta. And to get the total energy, we do total energy is mechanical energy plus non-mechanical energy. So kind of going on, piggybacking off the idea of the work energy theorem, the law of conservation of energy says that in an isolated system, and isolated is underlined there because it's important. If you're isolated, it means you're all by yourself. So our system, if it's isolated, there's nothing doing anything in or out of it. So it's all by itself. There is no outside entities. The system can't lose or gain energy. So that means that the energy remains constant. Another way you've probably heard it is energy cannot be created or destroyed, but can only be transformed from one type to another. You could also have it could transfer to another type, but the total energy still stays the same. So like the idea is that the energy of our universe is constant, and we just have to make a good accounting of it to make it work. So total energy initial equals total energy final. We don't have to always compare the initial and final. It's anywhere at any time. It's always the same number as long as it's an isolated system. And again, if it's not isolated, there might be work going in or out, but the total energy initial that you start with plus whatever change in work you have or change in energy you have, which is the work. And we'll practice some of these ideas. So plus the work, whatever that work is, it could be positive or negative or zero. If you don't have any change, then that means the total energy initial equals the total energy final. This formula just has to work out. So if I started with, say, 10 and I ended with 8, I would know that this work was a negative 2. If I started with 10 and I ended up with 12, this missing work here and this formula would be a positive 2. So it's just like, it just has to stay balanced. If it was 10 to start and it was 10 at the end, we know that the work done was 0. So it's just as simple as kind of keeping track. There's different ways to do that. We're going to write it as formulas. You're going to draw some pictures and look at different kind of charts and bar charts and pie graphs, but it all works kind of the same. So it says, when you're solving energy problems, you want to read carefully. That's always important. Identify your givens, draw a picture. So that's the first step in pretty much every physics problem we do, get a visual and an idea of what's going on. Determine the types of energy involved at different positions or times, initial and final, whatever 2 points you're comparing, point A, point B. You're going to set up a conservation equation, and it says include non-mechanical energy or work if necessary. And then you're going to solve for whatever's missing. So speed, height, the stretch, whatever idea they actually ask for in the problem. But this video is not dedicated to problem solving. It's really just dedicated to the concepts. All right. So let's talk about this example here. And it says a ball is being held above the ground, then it drops and falls straight down. Restrict your analysis to the ball before being in the air before it hits the ground. So going from here right until it hits the ground. So it's not hitting the ground there. I'm just going to label these with like A, B, and C. So we can kind of compare where the ball is at different points. And let's make a key for the different types of energy. So I'm going to say that gravitational potential energy is going to be in blue. And if we have any kinetic energy, that'll be in green. If we have spring potential energy, that would be in black. And let's make if we have non-mechanical energy, that would be in red. Okay. So if you think about point A up here, the ball is just being held up at point A. What kind of energy does it have there? And these are just pie charts. We're going to make pie charts for positions A, B, and C. So for A and B and C. All right, so at point A, I would say this pie chart would be all blue. So I'm going to get a better now. So this would be all blue. Why is it all blue? Because it's gravitational potential energy, and it's starting out being held. So if it's being held, it's not moving. It's just stationary. Okay, and so that ball only has gravitational potential energy. You let go and it starts falling. Okay, so as it starts falling, what happens to the blue? The blue is going to get smaller because what's happening to the height? It's getting closer to the ground. So as it moves closer and closer to the ground, that height decreases, which means that the UG is going to decrease. Now, the energy isn't transferring out of our system. Our system is just the ball and the Earth. So if that energy isn't transferring out, it has to change into something. So it has to change into another type of energy. So the type of energy is changing it is to kinetic. So it changes into kinetic energy because it starts moving. So as it falls, it starts moving. As it drops, we've already studied this motion. It goes faster and faster. So as we get closer to the ground, the kinetic energy is increasing more. So if I picked the very ending part, which might be the next part that I want to talk about, so C, I'm going to make that circle essentially all green. So, and the reason why I'm going to pick all green here is because it's no longer above the ground when it gets to the ground. So it's not hitting the ground yet. We haven't talked about that, but the height is essentially 0. So, so that's that. So it's got green energy. So all this red has changed into all green. Notice these circles are the same size. So that's true because they're supposed to be the same amount of energy. So B is sort of the tricky one. B is where you're trying to figure out, okay, what does it have? What kind of energy it has? So at B, I think it has more than one type of energy. So you're allowed to have more than one type of energy. It's got potential energy because it's above the ground. It also has kinetic energy because it's moving. So it's got two types of energy, and we just have to think about how is it distributed. So is it evenly split up or is it not evenly split up? So I would say it's not evenly split up because this doesn't look like it's fallen halfway. So I would say this might be halfway, and it hasn't reached the halfway point. So if it hasn't reached the halfway point, that means it has more height than half of it. So that means it has more than half gravitational. So I would say the gravitational potential energy is maybe slightly more than the other type. So that section of the circle might be the blue potential energy. And the other part, the part that's left over, that's going to be the kinetic. So some of it has changed into kinetic, but not all of it yet. And again, this is just qualitative. We're not worried about numbers yet. Eventually, we'll worry about the numbers. But the idea here is we just want to get a feel for how energy transforms or transfers in different situations. All right. So let's try another one. Same kind of idea. A ball is thrown up in the air. It falls back down. Velocity vectors beside each corresponding ball in the direction. Draw energy storage pie chart for each letter position. So we're going to do A, B, C, D, and E. And we're going to just say it's starting at the ground level to make it easier. So it's starting at the ground here. It's being thrown up. It's coming down. This is moving the whole time. So we're always going to have kinetic energy. So if we draw in the velocity vectors, the first velocity vector is kind of going up and to the right. The last one's coming down to the right. This is moving, and again, it gets slower. At the top, it only goes horizontally. We didn't really study, or we may have studied or projectile motion in the class that you're in, but I didn't in all of them. So as it goes up, it slows down. As it speeds up, or as it falls, it speeds back up. That's still true, just like it did in free fall. But the horizontal velocity stays constant. So it's got a velocity everywhere. So it's got a little bit of velocity everywhere. And we're going to talk about the energies again. So in the beginning, it's at the ground. So down here at position A, I would say it's all kinetic energy. And I'm just going to label with the letters instead of, so K or KE for kinetic. And that would be 100% of it. Okay. At B, it's got some kinetic. It's got a little kinetic. But it's got mostly, so maybe a sliver of kinetic. But most of it is UG. It's mostly got gravitational potential energy because it's height. At C, it's got almost all gravitational potential energy, so it's got an even smaller sliver of K, kinetic energy. So that's the kinetic energy part. And it's got a bigger part of UG. D, it seems to be about half the height, so it might have about half the gravitational and about half the kinetic. And then finally, it's back down to the last part at E, and that's going to be all kinetic again. These are identical circles because it's the same position right at ground level. So so those are there, and then again it's just redistributing the energies and trying to get it the right amount. All right. This last one here, the ball is hitting the ground. If you look at it, when it's hitting the ground, it's getting compressed. So that's a different type of energy that we haven't talked about yet. Also, you can see that it doesn't bounce up as high. So we want to figure out what's happening to that energy, where is it going into, and we'll talk about that. Just to talk about our system here, and I haven't pointed that out before because our system was just the ball and the earth and every other time. This time we're going to have the system be the ball, the earth, and we'll say the ground. All right. So the ground is the new factor in here because it's bouncing. And when it hits the ground, what happens when something runs into something else? So if I clap my hands, they're running into each other. You can tell that there's some kind of heat or sound generated in that point. There's also, well, you definitely can hear the sound. You can't hear the heat, but both of those are happening. So when we have heat and sound energy is that non-mechanical type. So the non-mechanical type is going to be present in this one. Also, when it's compressed here, that's going to be the spring potential energy. Even though it's not a spring, it's the elastic potential energy of that ball. So, so if we start out at the beginning, what kind of energy does it have in the beginning? I would call that just all gravitational. So that's UG. And again, you need the Earth to have gravitational potential energy. When it falls, it's coming down here to point B. Point B, I'm going to say it's actually stopped, and it's compressed at like the place. So it's changed into US, but it's also hit the ground, and there's some heat and sound, so it has the non-mechanical energy. So that non-mechanical energy is present. And with non-mechanical energy, one of the things that you can't really do, it's not easily transferred back into usable energy or mechanical energy. So that's why when it bounces up, it is not moving as much. Technically, if I was correct here, I should actually add kinetic energy to this because in order for it to go horizontal and go through projectile motion, it needs this velocity, and that velocity is constant. So the K is actually constant all the way through in this situation. So we got gravitational and kinetic at A. We got our spring potential and some kinetic because it's still going to the right, and all these at B. So this is A and B, and we're going to keep going with C and D and E. And it's going to kind of start repeating itself. So when it's back up at C, it's gravitational and kinetic and whatever non-mechanical energy that we had at point B. So like the non-mechanical energy at B is not changing. So like that is, you can't transfer it back into the potential or kinetic. So that's why, again, it goes lower. At D, it's got spring potential energy. It's got that little bit of kinetic still. And now it has a bigger amount of non-mechanical energy. And we know it's bigger because after that bounce, it goes up even a smaller position. So this non-mechanical energy is increasing as it bounces, and that's why it has less mechanical energy to bring it back into the air. And then at E, it's back to the same things. It's like spring potential energy, the little bit of kinetic, and then it just has the non-mechanical energy at point D. So that that value for the non-mechanical energy gets bigger and bigger because you have, every time it hits the ground, you have more heat and sound being the mechanical energy transforming into non-mechanical energy, and it keeps decreasing. Okay. In another video, we'll do some problem solving and get through that. So and we'll do some conservation of energy stuff. So have a good one, and I will see you guys later.